Okay, this is lesson 19, part B, factoring exponentials. We're going to start off with factoring stuff that hopefully you guys know how to factor. And then we're going to move on to factoring exponentials. And then I think it goes to the sum and difference of cubes. So the first thing we're going to talk about is what is an exponential expression. It's a base raised to a power. And factoring itself is we break up an algebraic sum into two or more factors, and we call those factors things that can be multiplied back together to get the original problem. Okay? So remember, when you factor something, factoring it into one or two or more sums that, when multiplied together, make the original problem back. So let's factor the first expression there. This one kind of goes back to old school. Kind of one of the first types of factoring you've dealt with, other than factoring a monomial out, right? When you factor monomials, your number one thing when I'm factoring anything is to look for common terms. Is there any common terms in x squared minus 7x plus 6? No, because x is not in the 6, so I can't. So there is nothing that's common between all three numbers. So I have to kind of go back to the idea that, hey, a is equal to 1. I like that. And so I think we should be able to say, hey, I can factor it possibly this way. The only way to get x squared is x and x, yes? And then you just have to ask yourself, what are the factors of 6 that will give me a 7? Only a 6 and 1. You got 2 and 3, but 2 and 3, when you add it together, give me a 5, right? That's not enough. So we know it's got to be a 1 and a 6. And then the problem is they multiply to get a positive, but have to add up to get a negative. Which means both of them have to be negative. So hopefully this is ringing a couple of the brain cells. They're vibrating in your head a little bit. Get the neurons firing again. Does that make sense? I could also go back and say, hey, find me the zeros, and that would be setting each one of those equal to 0. X would equal 1, and x would equal 6. Okay. Now, looking at our next problem. There's actually two ways to do this one. One is going to be a little bit more quicker or maybe easier than the other method in the long run. But I have 4m squared minus 16. We're going to use a little bit of this technique today, but with cubes. Isn't that a perfect square minus a perfect square? So I can handle it as the difference of squares. Or, wait a minute, first off, is there a common term? 4. So wouldn't it just be easier to say, hey, I can factor a 4 off. That leaves me with m squared minus 4. I think this would make my numbers smaller, make it a little bit more manageable. What do I need then, or what can I do now? I have a square minus a square still. Then I can can't just use the square root. Can't just factor off an m, or out an m. Difference of squares. I'm going to ignore the 4 out front for now. That's going to come along for the ride. You guys remember doing, hey, if I can fill this in, I'll know a and b. I ask myself, what's being squared to get m squared? M. What's being squared to get 4? 2. That tells me what my A and B terms are, because you guys should remember this. A squared minus B squared. What does that factor to? No, no, no. A, B, A, B. One of them is plus and the other one is minus. Right now, the M and the 2 in our problem is like A and B. So if you need to, go right underneath and put a little A, put a little B, which means this becomes M minus 2 and M plus 2. The order there with the plus and minus doesn't matter. One is just positive, one's negative. How do I know if I'm correct at any of these? Well, multiply them back together. You will get the original problem. Oh, wait. We're not technically done because we forgot to do what? We forgot something. I told we're going along for the ride and I forgot to bring it along. The 4. The 4 really should go up front. Now if we multiply all of that back together, we'll get the original problem. That last one down there, it's a little small on the screen for you guys. It's 12, x to the 7, y to the 4th, minus 15, x to the 5th, y to the 4th. Is it a perfect square? Minus a perfect square? Is 12 a perfect square? No. Is 15? No. Is x to the 7th a perfect square? No. But y to the 4th is. But since they're not a perfect square, then maybe, or no, then basically I know that I can't use difference of squares. What can I do then? Or what did I try to do with the first two problems right away? It says factor, look for. This is all review. Look for common terms, not denominators, but common terms. What's common? First of all, I'll look at the 12 and the 15. What can both give? 3. So I can divide it by 3. X to the 7 and x to the 5th. Everyone can donate. How many x's? 5. So the x to the 5th can be divided out. And y to the 4th. They both can give all of their y's. And what's left over when I divide that out? What's 12 divided by 3? 4. What's x to the 7th divided by x to the 5th? It's x squared. And y to the 4th divided by y to the 4th? Not 0, but 1, so we don't have to write it. Minus 5. X to the 5th divided by x to the 5th, y to the 4th, y to the 4th. They both cancel to 1. So there's my answer. Or is it my answer? I got x squared and a 4 in front. That's a perfect square. But is 5 a perfect square? No. So I'm done. Technically, there would be a way to factor that. If I had to find a particular answer and solve it, I would definitely just maybe end up with a square root of 5 instead of, a nice number. So there's ways to do that. But for our purposes, you're done. You factored it as far as you can go. So since we're working with those exponents, let's talk about what exponents are and how they work. What does it mean? What does it mean to be x to the 4th power? You have 4 x's. You have x times x times x times x, correct? That's what it means. Okay. What does it mean, or how can I simplify or change x to the 8m divided by x to the 4th? You got a common base. You're dividing the bases. What do you do to their exponents? What do you do to exponents when you have their bases the same? You subtract them. So if I subtract them, what do you mean? becomes x to the 8m minus 4, correct? So wait a minute, let's go the other way. What is 4 to the 2x plus 3? Then, what could that look like? Or should I let's jump over the 4 one. Let's go to 2. Because that's kind of like the exact example that we just did above. Can I change that to look like something else? Yeah, 2 to the 3x over 2 to the positive 6. Or, if I wanted to make it a negative 6, could I do it then as 2 to the 3x times 2 to the negative 6? Because what happens when you multiply their bases instead of divide? What do you do with exponent? You add them. So in this case, if I left it, instead of being subtracted on the bottom and make it positive, if I left it on top, it'd become negative. Does that give you a hint on what we can do with the 4? What's the 4 one going to look like? It'd be 4 to the 2x times 4 to the third. So I'm able to use my exponent rules in reverse or forwards, doesn't matter, no matter which way you're looking at it from, to expand, condense our problems. So for our problems, it might be very handy to go like the last 2 problems and expand things. Break them apart, break them up. So therefore, we can see all of their individual pieces because some of them have exponents, or have variables as exponents, and some of them, like 4 to the third power, is just a number. 4 to the third power is what? 64? Okay. Moving on. Let's take a look at these. So the factor of this one, my first hint would be to use the fact that we got a common base with exponents that are added, in this case added, sometimes they can be subtracted. Break them apart. So I'm not going to factor anything yet. I'm just going to simplify, or maybe unsimplify, maybe we'll call it. And so I'm going to have a 3 x to the 2n times what? X squared. Because x to the 2n times x squared becomes x to the 2n plus 2. And I'm going to do the same thing with the 12 side. So it'll be 12 times x to the 3n. X to the third. Now just remember that those are multiplied, so therefore I'm able to divide something out. Yes? Now wait. This could get a little confusing on the fact that I have x to the 2n and x to the 3n. I have an exponent that has some multiplication in there. Could I use this one? What's that exponent rule called? Power of power. And when it was a power of a power, I could multiply those exponents together, correct? Does it matter which one's the m and which one's the n? No. So technically, could I go in the reverse order? That's a bad arrow. That way? Because right now, I have something like x to the 2n. Could I change that so I can actually kind of see how many of these I have? Hence, I'll do the first one for you. Could I change this to x to the n squared? times x squared. Would that be okay? Because how many x to the n's do I have then? 2. So I know that I'll have at least up to 2 that I can donate or give away, right? What's the second one going to look like then? 12 n cubed times x cubed. So how many x to the n's will I eventually be able to get rid of altogether? Not 5. Only 2, because you have to. Remember, this whole idea of factoring is you can only give what everybody can give. So now we start the process. The process starts with the numbers. A 3 and a 12. Each one can give how much? 3. Okay. X to the n's, how many? 2, because the first one's got 2 of them, the second one's got 3 of them. And how many x's? 2. Essentially, we got rid of the whole entire first term, yes? Okay, that's what's all being donated. What's left over then when I donate everything of the first term? What has to be there? Really, what am I doing? I am dividing. So what is 3x to the n squared, x squared, divided by 3x to the n squared, x squared? 1. I need to have a placeholder, because eventually I would distribute that back in to get the original problem. Plus 12 divided by 3. X to the n cubed divided by x to the n squared. Not n. How many of them? There are 3 of them. I'm donating 2 of them. So I still have an x to the n, right? Can you guys see that? I'm going to change colors here so that I can. There are 3 of them, and I have to get rid of 2 of them. That still leaves me with 1 of them. And x cubed divided by x squared is x. And of course I can't leave my answer like this. That's not simplified. So now I have to go back and put everything together. This is a longer process, but it helps us identify where our things are coming from. Eventually, you hopefully will get to the point where you don't need to do this. But it's good to break it up if you can. So, on the outside, I definitely can see I have a 3. Can you guys put all of that outside stuff together to say it's x to the what? Not n squared. 2n plus 2. What's that? And then 1 plus 4 x to the n plus 1. I ran out of room, sorry. That's n plus 1. Now, if you were to multiply everything together, you get back to the original problem. So, if you look at a problem like that bottom one, and you get stuck, but you recognize that you have variables in your exponents, maybe change things around, like we did above. X to the 2a can be rewritten using that power of a power idea in the top corner. Could I change that to say x to the a squared? Would that be okay? Power of power still says that it would be x to the 2a, yeah? Could I do the same thing with the y? Oops. Would you guys be okay with that? Just changing the top. Wait a minute. That means I have a square minus a square. I'm going to use the difference of squares. And we just had that on the last slide. What is the difference of squares? A squared minus b squared, which is a plus b and a minus b. What's a and what's b in this case? It's not the a and b there.
And y.
It's x to the a and b to the y. So therefore, or y to the b, sorry. So therefore, it becomes x to the a plus y to the b times x to the a minus y to the b all over. And what do you see happens?
They cancel.
Yeah, they cancel. And so you're left with x to the a minus y to the b. Took 2 steps really to get to that point, but we kind of got scared. We got a little stuck in the beginning, but then all of a sudden we start to mess with it just a little bit, change things around so that we know we got our numbers separated from our variables possibly. Turns out to be not so bad of a problem. Last part C, is the sum and difference of cubes. The same exact way that I presented the difference of squares. Now remember, there was no sum of squares. There's only difference of squares. But here, we do have a sum and difference, which means add and subtract. You need to recognize that you have a binomial, 2 terms, made up of perfect cubes. And if you do, you can use those 2 formulas. A cubed plus b cubed is equal to, you can factor it, a plus b times the quantity a squared minus ab, a squared minus ab plus b squared. Or if it's a cubed minus b cubed, it's a minus b times the quantity of a squared plus ab plus b squared. It's the exact same layout, but you change 2 signs. If you have a sum, your first term is a plus b, but inside the second set of parentheses becomes a squared minus the ab. Versus if it's a difference, if it's an a minus b on the outside, and then it becomes a squared plus ab. So if you want to only remember one formula, you just need to remember that small change. Okay, so I got 4 steps to make this work, and these are the same 4 steps if it was a difference of squares. So in step 1, it wouldn't have a parentheses with a cube on it. It would have a parentheses with a square on it instead. But I'm using the same idea that we just used twice in our notes already, is you set up the parentheses with something cubed, plus or minus, according to what the problem is, something cubed. Find out what is being cubed to get to that answer. You can do that by just simply taking the cube root. Before we took the square root of both of our terms. Now you take the cube root, or to the 1/3 power if you need to do that on your calculator. Okay? Those are your A and B's. You plug those into the appropriate formula on the left or the right. That's as simple as it can get. Now, is it going to stay perfect with nice little small numbers like x cubed minus 8? No, it's going to throw stuff at us that are complicated with multiple variables. But you just have to know your exponent rules, and know your substitution properties, all of those things, and you're good to go. First problem that we are going to attack here is x cubed, y cubed, minus p cubed. What we need to recognize, there are 2 terms, and the 2 terms are perfect cubes. Because x cubed, y cubed is perfect cubed, and p cubed is a perfect cube. So, set it up. Something cubed minus something cubed. I chose minus this time because there's a minus sign. I know. So what's being cubed to get x cubed, y cubed? xy. Because a power of a product would tell me I would take that cubed and basically distribute to the x and the y. What's being cubed to get p cubed? P. We now know A and B. And when we know A and B, we can plug them into our appropriate formula. Which one, see if you guys can do it without looking back, which one is the appropriate formula? A minus B times A squared, what's the change? Plus AB plus B squared. We just have to plug it in there and simplify. We're done. So let's make that happen. XY minus P is XY squared. Notice I put parentheses around that XY every time I use it, because I'm basically using substitution now. And at this point, when I use substitution, I use parentheses so I don't lose signs and I don't lose my numbers. Yeah? Plus parentheses XY and parentheses P plus P squared. So we just have to simplify that longer parentheses because xy minus p is already simplified. So xy minus p, and when I square xy, I end up with x squared y squared plus xyp plus p squared. That, girls and boys, is your answer. Here's the cool thing. Here's the cool thing about factoring a perfect cube. Okay? Listen to this, because this is going to be very helpful. The longer set of parentheses there with the a squared and the b squared and the ab is never factorable. You will never be stuck trying to factor that second half. This thing will never be factorable. It'll not give you nice numbers, ever, okay? They always will be imaginary solutions to that if there were going to be nicer numbers. So be very careful on that. Okay? The last one is the exact same way. Let's just set it up. The only difference is that this one uses a plus. I think the last one's the easy one. What's cubed to get x cubed? X. The first one, to get 8, it's a 2. To get m cubed, m. To get y to the 6, how do I get y to the 6 when cubing? It is y squared, because y squared cubed, you multiply 2 times 3, which is 6. You now have an a and a b. Plug it into the correct formula. Homework is on page 143. This is lesson 19 and 10 through 14 and 20. Have a fantastic day.